In section 4.2, you will learn about sigma notation and area. First up, let's review sigma notation, which you actually first learned about in your college algebra class. So you will get expressions that look like this, and the way you read that is to say the summation I equals 1 to n of a sub I, where 1 is what's called the lower bound and n is the upper bound. And this big capital sigma stands for the operation of summation. And what this means to do, a summation from I equals 1 to n of a sub I means you're going to take a1 plus a2 plus a3 plus and so on, plus a sub n minus 1 plus a sub n. So you go all the way to the upper bound. And each of these a sub I terms is the ith term of a sum. So a1 is the first term of the sum. a2 is the second term of the sum. a3 is the third term of the sum. an is the nth term of the sum. So first I just want to help you get a little bit of experience with it. In this example, we have to find the sum. We are given the summation I equals 4 to 8 of I squared. So what that means is a sub I, the ith term, just says to take the term number I and square it. So we are going to take a4 plus a5 plus a6 plus a7 plus a8. And that's what this means. Take these terms and add them up. And to figure out the value of each of those terms, take the term number, the I, the subscript, and we square it. So a4, just meaning the fourth term, is going to be 4 squared. And we have to add to that the fifth term, which we know is you take the term number and square it. And the sixth term is going to be 6 squared. And the seventh term will be 7 squared. And the eighth term is 8 squared. And then it's just a matter of adding up all those values, and this equals 190. So the outcome of a summation, when we know what the terms are, is a numerical value. In this example, we have to write using sigma notation this sum, where we have 5 halves plus 10 thirds plus 17 fourths plus 26 fifths plus 37 sixths. This time we are given the terms being added, and we have to come up with the sigma notation that would lead to that. So we know this will be some kind of summation, and it takes a little practice to get good at making the summation symbol. And it's going to be I equals whatever we decide the lower bound is to whatever we decide the upper bound is of whatever we decide the ith term is. So looking for patterns here, we can see the denominators going 2, 3, 4, 5, 6. So that certainly looks like we could have I in the denominator if we let I go from 2 to 6. Then what we want to do is see what the relationship is how do we get from I equals 2 to this numerator of 5? Or from I equals 3 to this numerator of 10? Or from 4 to 17? And you may see that pattern already. All the numerator is taking the denominator, squaring it, and adding 1. 3 squared is 9, add 1, you get 10. 4 squared is 16, add 1, you get 17. So the numerator is just I squared plus 1. So that means we know that the ith term of the sum, a sub I, is equal to the quantity I squared plus 1 over I. So one of the things you have to get fluent with is, given the summation notation, come up with the terms, or given the terms, come up with the summation notation. Next up, we're going to review the summation formulas you learned back in your college algebra class. And I think the best way to review them is to just dive right into these examples where we have to find each sum. In this first one, we have the summation I equals 1 to 7 of 8. So 8 is a constant, and so the formula that will help us solve this one is this very first one where we are summing over a constant. And the rule says is that the summation I equals 1 to n of c is just equal to c times n. So all we have to do here is take c times n. It's kind of a good idea to notate what it is you're doing. And that means we will take our constant, which is 8, times n, which is the upper bound, 7. So that means the summation I equals 1 to 7 of 8 is just equal to 56. Next up, we have the summation I equals 1 to 5 of 2 times I. Now, there's some properties here that tell us if we have a constant multiplying each of the terms in the summation, we are allowed to bring that constant out in front of the summation and then just do the summation over the terms, a sub I. So in this case, we're going to apply this property over here, and we know that means we can bring the 2 out front, and this becomes the summation I equals 1 to 5 of I. Now this is something we have a rule for. It's right here. So this is going to be 2 times, we're going to apply this rule, which for summing over I is n times n plus 1 over 2. And this becomes our n right here is 5. Then that means n plus 1 is going to be 6, and we have to put that over 2. So then when we simplify this, these 2's are going to cancel, and we are left with 30. Next up, we have the summation I equals 1 to 4 of I cubed. Summing over I cubed, we have a rule for that, and that rule is we have to do n squared times n plus 1 squared over 4. So we will get a rational expression. We have to take n squared So our upper bound is 4, and we have to square that. Then we have to multiply that times n plus 1 squared, which would be 5 squared. And then in the denominator is 4. Now, it's important for you to understand that this 4 in the denominator of the rule doesn't have anything to do with the 4 being the upper bound. That's just a coincidence. So now we know 5 squared is 25. One of these 4's will cancel. So we just have to do 25 times 4, which is 100. In this example, we have to find each sum. First up, we have to do the summation I equals 1 to 10 of the quantity 3i squared plus 4. Now let's bring up our summation formulas and properties. And we see that if we are summing over a sub I plus b sub I, we can break that up into the sum of a sub I plus the sum of b sub I. We also recall that if we have the summation of a constant times a sub I, we can pull that constant out front. So let's rewrite this as 3 times the summation I equals 1 to 10 of I squared plus the summation I equals 1 to 10 of 4. Now be very careful to notice that the 3 only multiplies this first sum, because in the original problem the 3 only multiplied the I squared. So we will have 3 times. We have to look to our summation formulas. We know that summing over I squared means we will be doing n times n plus 1 times 2n plus 1 over 6. So in our case, n is equal to 10, so that means we have to do 10 times n plus 1, which would be 11, times 2n plus 1. If we double 10, we get 20, and then we add 1, we get 21, and we have to take that over 6. Plus, we have the summation I equals 1 to 10 of 4, and we know that that rule tells us to take c times n, so that means we're going to do 4 times 10, and then we can just grab our calculators to discover that this is equal to 1,195. Here, we have to do the summation I equals 1 to 20 of I squared times the quantity I plus 1. Now, none of our formulas will allow us to do this summation in this form. So what we will need to do is distribute that I squared into this binomial. So now we have the summation I equals 1 to 20 of the quantity I cubed plus I squared. Now, because we have a sum in here, we can break this up into two summations. So we will do the summation I equals 1 to 20 of I cubed plus the summation I equals 1 to 20 of I squared. Now, referring to our rules, we see that for summing over I cubed, we will have to do n squared times n plus 1 squared over 4. And for summing over I squared, we will have to do n times n plus 1 times 2n plus 1 over 6. So let's continue here. Doing this first summation over I cubed, we have to take n squared, so 20 squared, times n plus 1 squared, which is 21 squared, divided by 4. For this second summation over I squared, we will have to take n, which is 20, times n plus 1, 21, times 2n plus 1, 41, and divide that by 6. Then we just need to pick up our calculators and do this calculation. So why don't you pause the video now and try this calculation on your own, then play the video again once you're ready to check your answer. And this sum works out to be 46,970. So these sums really start to add up quickly. Now we're ready to try an example that involves some calculus. Here we have to find the limit as n goes to infinity of s of n, where s of n is given to us to be this expression. So we've got the limit as n goes to infinity of 64 over n cubed times n plus 1 times 2n plus 1 over 6. And remember, the limit is applying to this entire expression. Now this will equal the limit as n goes to infinity. Let's do some simplifying here. We have an n here that will cancel one of the n's down here, and that will become n squared. We also have coefficients of 64 and 6, and they have a common factor of 2. We know 2 goes into 6 3 times, and 2 goes into 64 32 times. So we can rewrite this in a simplified form as 32 over. Now instead of having the n squared underneath the 32, I'm going to switch places with the n squared and the 3. We are allowed to do that, so we can put the 3 here, and we're going to put the n squared underneath the rest of this algebra. And I'm also going to multiply out these two binomials. So first times first gives us 2n squared. Now let's do the outer and inner terms all at once. The outer term would be n. The inner term would be 2n. So adding n plus 2n means we're adding 3n. And then last times last is plus 1. Now remember, in the denominator, we're going to write that n squared. So once again, let me remind you, all we did in the denominator was switch places with the 3 and the n squared, and we're always allowed to do that with rational expressions. Now, if we were to try evaluating this limit right now, plugging n going to infinity into this numerator would give us infinity in the numerator. Plugging n going to infinity into the denominator would give us infinity in the denominator. And we know that infinity over infinity is indeterminate. So we have to do some algebra here and simplify it into a form that we can evaluate. Now remember from chapter 1 that if I have a constant inside the limit, that constant can get pulled out front. So let's do that, and we'll have that 32 over 3 that we write out front, and then that will be times the limit as n goes to infinity of this expression inside. Our technique here will be similar to how we evaluated horizontal asymptotes. We can see this 2n squared over n squared will simplify to 2, plus we have 3n over n squared simplifies to 3 over n, and finally 1 over n squared means we add 1 over n squared, close the bracket. Let's bring down our equal sign and the 32 over 3, and now we can let n go to infinity. We know that 3 over n, if n is going to infinity, is going to go to 0, and 1 over n squared is also going to go to 0 as n goes to infinity. So the only thing left from inside the brackets is the 2. And now we can simplify this. Remember, the 2 only multiplies the numerator, so we have 64 over 3, and this is our final result. In this section, you will learn to approximate the area under a curve using rectangles. Here, we want to shade in the area bounded by f of x, which is this curve over here, the x-axis. Now, remember, the x-axis is just a line whose equation is y equals 0, so that's this. It's also bounded by x equals a and x equals b. Now these two are just equations of vertical lines. So x equals a is this line, and x equals b is this vertical line. And now we want to shade in the area that's bounded by y equals f of x, the x-axis, which is y equals 0, this vertical line, which is x equals a, and this vertical line, which is x equals b. So grab your highlighter and let's color in the shaded area that we are interested in. We can use rectangles to approximate the area under a curve on the interval from a to b. If we let n equal the number of rectangles, then the width of each rectangle will be delta x, which is the width of the entire interval, b minus a, divided by the number of rectangles, which is n. So if we have n rectangles, then the width of each of those rectangles is going to be delta x. A lower sum uses the areas of inscribed rectangles to approximate the area under f of x. Let's take a look at this diagram here. The area under f of x has been divided up into 1, 2, 3, 4, 5, 6 regions. That tells us that n is equal to 6. The number of rectangles we are going to make is 6. Now, inside each of those 6 regions, we have to draw an inscribed rectangle. In region number 1, the inscribed rectangle would look like this. Now, notice that the height of the inscribed rectangle is the y value right here. Now, what we call the x values are lowercase m sub I. So this would be lowercase m1 because it is the x value we are going to use to plug into the function so that f of m1 gives us the height of the rectangle in region 1. That's what this sentence right here is saying. The m sub I are x values selected so that y equals f of m sub I yields the height of an inscribed rectangle. Here, m1 is the x value so that y equals f of m1, which is this height, gives us the height of our inscribed rectangle for region 1. Now in region 2, we have to pick this x value right here for m2 so that the height of the rectangle becomes f of m2, and then this would be the area under the curve. Now these are inscribed rectangles because they live completely inside the curve. There's no part of the rectangle that goes beyond the curve. In region 3, we have to pick this x value because then the height of region 3 would be f of m3. Now notice for region 4, we actually have to pick this same x value again. I can't pick this x value over here because the height of that rectangle would go outside of the area under the curve. So to get the inscribed rectangle for region 4, I have to use this x value, which yields this height. For region 5, we have to pick this left endpoint for our x value so that the height there gives us the inscribed rectangle. No part of our rectangle can go beyond the height of the curve. And in region 6, we have to pick this left endpoint here, and we get the height of our rectangle is f of m6. Now the areas of these 6 rectangles will approximate the area underneath f of x. And to do that, we just take the sum of the areas of the rectangles. We know the area of a rectangle is just base times height, which would be delta x is the base, f of m1 is the height. And I'm going to choose to write it in this order. F of m1 times delta x. we have the base, delta x, times the height, f of m1. Now for region 2, we have the base is delta x and the height is f of m2. So I will write that as f of m2 times delta x plus, for region 3, then the area of this rectangle will be f of m3 times delta x plus, for region 4, that height will be f of m4 delta x. We add in the area of region 5, which would be f of m5 delta x, and then region 6 will be f of m6 delta x. Now, a way we can combine all of that together is to use a summation. The summation I equals 1 to 6 of f of m sub I delta x. This summation says I'm going to add up the areas of 6 rectangles, taking the base times the height of each one. So this is what's called the lower sum, and it's referred to as lowercase s of n, and so in general it will be the summation I equals 1 to n of f of m sub I delta x. And remember, the m sub I are x values selected so that y equals f of m sub I yields the height of an inscribed rectangle. All the rectangles in the lower sum have to live completely inside the area under the curve. And you choose either the left endpoint or the right endpoint of the interval so that the height at that x value stays inside the area under the curve. Now the upper sum uses the areas of circumscribed rectangles to approximate the area under f of x. This time, capital M sub I are x values selected so that y equals f of m sub I yields the height of a circumscribed rectangle. Now remember, we had 6 regions, which we can label again here, 1, 2, 3, 4, 5, 6. And in region 1, we will have to use the left endpoint over here, capital M1, which gives us this height, so that we get this rectangle, which is the circumscribed rectangle. So this time you choose either the left endpoint or the right endpoint, whichever one gives you the rectangle that actually goes outside of the area under the curve. And the total area will be the sum of the areas of the rectangles. So in this case, we will have 6 rectangles, because once again, n is equal to 6. So the area of rectangle 1 is going to be f of capital M1 times delta x. And once again, that's just the base of the rectangle, delta x, times the height of the rectangle, f of capital M1. Then we will add to that the area of region 2. Here we have to pick this x value for capital M2, so that the height, f of m2, gives us this rectangle. So f of m2 delta x. We will have to add to that the area of region 3. Now to get the circumscribed rectangle in region 3, we have to pick this x value for m3, so that y equals f of m3 is the circumscribed rectangle. So we add f of capital M3 delta x plus, for area 4, notice we will need to skip over this x value and choose this x value for capital M4. So that f of M4 gives us the circumscribed rectangle. So we add f of capital M4 delta x plus, in region 5, we have to choose this x value, and we get the height to be the circumscribed rectangle. So f of m5 delta x plus, for region 6, we have to choose this x value to get the height of the circumscribed rectangle, f of capital M6 delta x. And we can write this as a sum. I equals 1 to 6 of f of capital M sub I delta x. This summation says we will add up the areas of 6 rectangles. This is base, this is height. So in general, the upper sum, noted by capital S of n, is going to be the summation I equals 1 to n of f of capital M sub I delta x. And remember, the capital M sub I are x values selected so that y equals f of capital M sub I yields the height of a circumscribed rectangle. Now, one thing you notice is that the area of the rectangles in the upper sum are going to combine to give us an area that's larger than the area underneath f of x. And if you compare that to the lower sum, you can see that the rectangles in the lower sum are going to combine to give us an area that's smaller than the area underneath the curve. So in general, we say that the lower sum will be less than or equal to the actual area under f of x which will be less than or equal to the upper sum. In this example, we have to use the lower sum and upper sum to approximate the area under f of x equals 3x minus x squared on the interval 1 to 3 with n equals 4. We can make a quick sketch of f of x. We know it's going to be a parabola that opens downward. We can find its roots very quickly by factoring out an x, and we have left 3 minus x. So we know there's a root at 0 and a root at 3. We know the vertex is always halfway between the roots, so the vertex is going to be here at 3/2. And we can find the y-coordinate of the vertex by plugging in f of 3/2. We can plug in either to the first form or the second form. I kind of like this second form because plugging in 3/2 for x right here, and then here 3 minus 3/2 is 6/2 minus 3/2 is also 3/2. So the y value is 9/4. So we can plot that point, 2 1/4. Now to get an accurate curve, we could plug in a couple values that are real easy to do, like f of 1 we see would be 1 times 3 minus 1, which is 2. So 2. And due to the symmetry, we know we're going to get the same thing when we plug in f of 2, but we can check. 2 times 1 is 2. And now we kind of get a nice shape going. Now our interval that we're working with is 1 to 3, so we know that means A equals 1 and B equals 3. So we're going from 1 to 3. Now because n is equal to 4, that tells us we will have 4 rectangles or 4 regions. And we know that delta x is equal to b minus a over n. So that's going to be 3 minus 1 over 4, which is 2 over 4, which is 1/2. So that is the width of each rectangle. So remember, we're on this interval 1 to 3 with n equals 4. So that means we can mark off the 4 regions that we're going to have. 1, 2, 3, 4. Each region has a width of 1/2. We might as well fill in this x value. We know it's 2 1/2, which would be 5/2. So now we're ready to do the lower sum, and we know that that's lowercase s of 4. We're going to have 4 rectangles, and that means we are doing the summation I equals 1 to 4 of f of little m sub I delta x. And remember, we are choosing the m sub I, which are x values, so that we get inscribed rectangles because it's the lower sum. So now what we have to do is add up the areas of the 4 rectangles that get formed from the inscribed rectangles. So we will have region 1, region 2, region 3, and region 4. In region 1, we have to pick the x value that gets us the inscribed rectangle. So here we have to pick this left side, because if we pick this right side point, we would get a rectangle that goes above the curve, and that's a circumscribed rectangle. So we're going to have to pick for the height f of 1 so that we get this rectangle. So we will have f of 1 times delta x, which we know is 1/2. And we have to add to that the area of the rectangle in region 2. Now in region 2, we can't use the left endpoint because that would give us a height that goes outside of the area under the curve. That would be a circumscribed rectangle. So we will choose f of 2 for our height so that we get the inscribed rectangle. So that will be f of 2 times delta x, which is 1/2, plus region 3, we will choose the right endpoint, x equals 5/2, and that will give us this inscribed rectangle here, times 1/2. Maybe I'll move these over. And then we have to add in region 4. Now you have to be careful in region 4. Sometimes students are tempted to use this left endpoint, but look what would happen. We would get the circumscribed rectangle, so our only choice is to use this right endpoint, f of 3. And that's okay that it's on the x-axis. We take that times delta x. So now we see all of these have a 1/2. Let's go ahead and factor that out front. So then we would have f of 1 plus f of 2 plus f of 5/2 plus f of 3 on the inside. We continue to bring that down, 1/2 times. Now we just have to figure out these values. F of 1, we already figured out, is equal to 2, so we can plug that one in. F of 2, we also figured out, was also 2. F of 5/2, we need to figure out. And I like to use this factored version. So it would be 5/2 times 3 minus 5/2. So 6/2 minus 5/2 is 1/2. So that's just 5/4. And f of 3 we know is 0. So we have 1/2 times, well, it looks like our common denominator will be 4. So we have 8/4 plus 8/4 plus 5/4. So that becomes 1/2 times 21/4. So that means our lower sum is equal to 21/8. Now we are ready to do the upper sum, which we know is capital S of 4, which will be the summation I equals 1 to 4 of f of capital M sub I delta x. And remember, those are going to be the circumscribed rectangles. Now let's get our drawing going again. We know the vertex was at 3/2, 9/4. We had f of 1 was 2, f of 2 is 2, f of 5/2 was 5/4, so 1 1/4. We had a root at 0 and a root at 3, so it just takes a couple seconds to get our graph back going, we know that our interval is from 1 to 3 with delta x, which we know is 1/2. Now when we do the upper sum, we know that we have to add up the areas of 4 rectangles, and that's going to be in our regions 1, 2, 3, and 4. So now this upper sum is going to equal, well, let's make a note that we'll find the area of rectangle 1, of rectangle 2, of rectangle 3, and rectangle 4. So in region 1, we have to choose the rectangle that will be circumscribed. So that means we have to choose the x value of 3/2 so that we get the rectangle that actually goes outside of the area under the curve. So we will be doing f of 3/2 times delta x, which we know is 1/2. And we have to add to that the area of rectangle 2. And in region 2, once again, we need the circumscribed rectangle. So that means for region 2, I can't pick f of 2 because that would be an inscribed rectangle. I have to pick f of 3/2 because that gives me the circumscribed rectangle. So we will do f of 3/2 times delta x, which is 1/2. We have to add to that the area of the rectangle in region 3. That's circumscribed. So to get that rectangle, we have to pick this left endpoint of f of 2. So we'll have f of 2 times 1/2. And we will add to that the area of the circumscribed rectangle in region 4. And for that, we have to use an x value of 5/2 so that we get the circumscribed rectangle here. So f of 5/2 times delta x, which is 1/2. Now, just like we saw with the lower sum, we can pull out this delta x from every term. So we will pull out 1/2, and we will have left f of 3/2 plus f of 3/2 plus f of 2 plus f of 5/2 equals 1/2 times f of 3/2 we know is our vertex, which we already figured out is 9/4. So we have 9/4 plus 9/4 plus f of 2, which we figured out earlier. F of 2 is equal to 2. Plus f of 5/2, which we also figured out earlier. F of 5/2 is equal to 5/4. We have a common denominator of 4. So from these two, we already have 18/4 plus, we would write 2 as 8/4 plus 5/4. This is going to be 1/2 times 18 plus 8 is 26 plus 5 is 31/4. So we get that the upper sum is equal to 31/8. Remember the lower sum, which we said was 21/8. That's the lower sum. is going to be less than or equal to the actual area under f of x, which will be less than or equal to the upper sum, which we just found was 31 over 8. Later on in this section, we're going to learn how to find the actual area under this curve.